Share your screen.
Let's see if it works this time. Oh, okay. Still not working. Okay, so I have to do a backup option. It's nice to see all of you, even through the black boxes on the computer. Let's see. See, actually, sorry. That did not work.
Sorry, that worked. We were seeing two screens, but that worked.
Okay.
I think you just have to mirror displays. If you go to displays, they are probably not mirrored. So if you mirror displays and then try again, I think it should work fine.
Let's see. I've been teaching a course for the last 8 weeks and did not have any problems the entire time with sharing Zoom. Let's see. Okay, let's try this one more time. My apologies again. Okay. Can you see that?
Yes, perfect.
Okay, wonderful.
Yeah. I think take it away, Kristan. The virtual floor is yours.
All right. Well, many thanks to the organizers for putting this together in these trying times and also for giving me the opportunity to speak today. I'll be discussing results in a series of papers co-authored with Jordan Cutler, an excellent postdoc at Harvard, over the course of the pandemic. And we have a lot of ground to cover, so let's get to it. So the past few years have seen a suite of recent developments in soluble models of 2D gravity. And space-time wormholes have been one of the key figures in those works. You know, for instance, wormholes yield non-perturbative effects in Joukey-Titebuoyant gravity, informing us that the dual of JT gravity is an ensemble of Hamiltonians rather than a single quantum mechanics. And further, they describe the statistics of that ensemble. And that's only scratching the surface. They've played a key role in many more developments, at least within the friendly confines of 2 space-time dimensions. Of course, one of the reasons why many of us started studying JT gravity and its cousins was to learn lessons that would ultimately apply to higher dimensional gravity. With that in mind, the main goal for today is to develop machinery to study Euclidean wormholes in more than 2 dimensions, including in lamppost examples of ADS-CFT, like 10D supergravity on ADS 5 times S5. Now, we are well used to the story of black hole thermodynamics in Euclidean gravity. Goes back to the 70s. The Euclidean black hole amplitude with a boundary of the form of a thermal circle times some space, say a sphere, it encodes an approximation to the density of states of the black hole. Classical gravity doesn't describe the precise details of the microstate spectrum, of course, whose level spacings one expects to be non-perturbatively small in a UV complete theory of quantum gravity of order e to the -1/g Newton. but it's good enough to describe the coarse-grained approximation. What we do is to find Euclidean wormholes which interpolate between two asymptotic regions, each with the same sort of boundary, thermal circle times some space. Besides finding these wormholes, our main result is to present evidence that these wormholes encode an important feature of black hole microstates, a coarse-grained approximation to the 2-point level statistics. In particular, we find evidence for long-range repulsion in the microstate spectrum. In fact, it's very reasonable to expect such repulsion. If you put a large N holographic CFT on a sphere, then you effectively have some complicated many-body Hamiltonian with a large number of degrees of freedom. And generic many-body Hamiltonians have a chaotic spectrum of energy eigenstates. So it seems reasonable to say that this applies for the unprotected part of the spectrum of n equals 4 on a sphere. Now, by chaotic, I mean that there's short-range repulsion between neighboring energy levels, which builds up to long-range repulsion. Both the short and the long-range repulsion are nicely diagnosed with something called spectral form factor that Steve Schenker nicely summarized in his talk a few days ago, appeared in Clifford's just now, and so on. It's, if I was doing this on the iPad, I could actually highlight it on the screen where it is. It's this thing, the z of beta plus it, beta minus it. It's this two-partition function object. There's some real-time evolution t in there, along with an inverse temperature beta to tame contributions from high energy states. The spectral form factor has some features which are robust for many different quantum systems. At early times, it dips on this plot here between times of order 1 and 10. But then at late times, it oscillates wildly. Now, if you perform either a rolling time average or a small ensemble average, then that's sufficient to smooth out the wiggles, and you end up with a smooth curve like the black one here. The long-range repulsion corresponds to this regime where this, again, I wish I could draw on here, where the black curve is increasing, it looks linear, and actually is linear, even though this is a log-log plot, so that growth is linear in time t. And then it levels off to a plateau at late times, which follows from underlying discreteness of the spectrum. Now, our wormholes that we consider being a two-boundary quantity are computing a contribution to ZZ. And so if we continue the inverse temperatures on the two boundaries, beta 1, beta 2, in this way, beta plus it, beta minus it, then these wormholes are contributing some non-perturbatively suppressed contribution to spectral form factor. However, at late enough times, that contribution is actually larger than the leading disconnected contribution that you get from summing over saddles. We can then look for a ramp coming from these wormholes. Now, the central problem we run into is that these wormhole amplitudes are they're non-perturbative effects in gravity, akin to instanton corrections. But unlike instantons and 40 Yang-Mills, these amplitudes lack a saddle point approximation. And in fact, one can prove this statement thanks to a theorem of Witten and Yau. In the absence of saddle points, we can choose to either give up on the problem or to persist. We're stubborn, so we persist. And our approach is, in a nutshell, to take Einstein gravity seriously as an effective field theory and to imitate what we would have done were this a problem in quantum field theory. At least as long as we can remain in a regime where an effective field theory description is valid. In particular, we adapt methods from field theory that have been developed to tackle analogous problems. Instanton corrections when there's, strictly speaking, no instanton solution to the field equations. All right, here's the plan for the rest of the talk. That was the introduction. Next, I'm going to discuss a particular wormhole amplitude in pure 3D gravity where life is sufficiently simple that we can compute at loop level. From there, I'll discuss wormholes in Einstein gravity and ultimately in Tendi supergravity. We'll continue with pure 3D gravity. There's been an expectation dating back to Maloney and Witten that 3D gravity with negative cosmological constant is inconsistent as a theory of quantum gravity. This has been revisited recently, And there's now an open conjecture that 3D gravity is consistent, after all, dual to an ensemble, where the non-unitarity identified by Maloney and Litton is healed by a sum over all three manifolds. Given that we don't have control over a single chaotic C greater than 1 CFT, it isn't clear if a dual ensemble even exists, but nevertheless, we can proceed by trying to make sense of the sum over three manifolds, i.e. to do gravitational computations as best we can. Now, if one takes this conjecture seriously, then you would arrive at the following dictionary between bulk and boundary. If you fix a boundary, say torus of complex structure tau, and then fill it in all possible ways, well, what is that? Well, that's the average partition function in the dual. You fix two boundaries and fill them in all possible ways, and that's the average 2-point function, and so on. With this in mind, we focused on a particular two-boundary amplitude, which would contribute to the variance of partition function. And the simplest topologies for such a wormhole that we can consider, well, they're of the form Riemann surface times interval, where the interval is the radial direction. Since the torus partition function has the state counting interpretation, we focus on the case where this Riemann surface is a torus, so that we can use the wormhole to diagnose level statistics. So we would like to compute the torus times interval amplitude of pure 3D gravity. This amplitude has no saddle point approximation, and so requires some care. Here's the brief version. We pass to a first order formulation of 3D gravity, where one integrates over Dreibein and spin connection instead of over metric. And we take advantage of the fact that torus times interval is topologically the same thing as annulus times circle, which we can think of as a Euclidean time. And then in first order, the time components of fields, the Dreibein and spin connection, they appear linearly in the bosonic part of the gravity action before worrying about gauge fixing. And so they act as Lagrange multipliers, at least to one loop order anyway. So integrating them out enforces constraints, which in 3D we can solve. We can completely solve them. And we can then perform functional integral over the constrained space. And the result is this formula in the blue box. Now, if you stare at it a bit, you'll notice that there's a single Maloney-Witten-like modular sum. But even so, this expression is in fact invariant under independent modular transformations acting on tau1 and tau2, the two boundary complex structures. So and this is great. From the 3D point of view, this had to be the case. And the fact that it is for this amplitude poses a very strong consistency check on our result. In fact, using some physical inputs from 3D gravity, we designed in a paper that followed up shortly after this one, an unconventional modular bootstrap, which was able to yield precisely this result for this amplitude up to normalization. That is, this amplitude is almost completely determined really by symmetry and consistency conditions. Okay, well, what was the point of this? Well, we wanted to study spectral statistics that's encoded in this result. Because in the many-body quantum system, different energy eigenstates, which are related by symmetry, well, related by symmetry, they don't repel, we decompose this result into contributions coming from different superselection sectors, which in this setting means primaries at fixed spin. Doing this yields a rather intricate result, which at low temperature assumes a very simple form that I presented here. There's corrections which come from this SL2Z sum. This is the order 1 minus beta on the slide, and they're somewhat complicated, but we have some handle on them. The dots indicate contributions from other three manifolds, which we know much less about. Now, the leading behavior is something the square root beta 1, beta 2, blah, blah, blah. Well, this is something that will look very familiar to those of you who are familiar with random matrix theory and the guts of JT gravity. It's precisely what one would find in a random matrix theory ansatz imposing Virasoro symmetry. And when I say precisely, I really mean it, like including the factors of 2 pi. This result, then, if you stick in beta 1 is beta plus IT, beta 2 is beta minus IT, well, it gives you Lorentzian spectral form factor. And, well, when you do that, you find a ramp. The square root beta 1, beta 2 is approximately t, and all the other contributions are subleading at large Lorentzian time. So you get something that grows linearly in t. And well, that's a ramp. From this, we infer long-range repulsion in the spectrum of BTZ microstates. So putting this together, this is perhaps the best evidence yet for an ensemble dual then to pure 3D gravity. This is kind of a smoking gun, which, if it exists, would evidently be some generalization of random matrix theory. Okay, let's move on to discuss wormholes in Einstein gravity. As I mentioned earlier, the vanilla sort of wormholes that we're interested in with S1 times a sphere boundary, well, they're not solutions to Einstein's equations. So what do we do? Fortunately, there's some history in quantum field theory of computing instanton amplitudes where there's no saddle to expand around. And most work in this vein falls under the moniker of method of constrained instantons. And a standard example is 40 Yang-Mills in the Higgs space. In that setting, there's no finite energy instanton solutions to the field equations, finite action rather, but there's still instanton-like corrections to amplitudes. And so to study these non-perturbative corrections, there was an idea that was originally suggested by 't Hooft and then developed later by Affleck and Affleck-Dine-Seiberg, which is the following. Take a quantum field theory with some fields phi, for which you don't have a saddle point approximation, and then foliate the integration domain by constant values of some constraint functional, mathcal C. For an intelligently chosen constraint, even though the full integral doesn't admit a saddle point approximation, the integral along one of these slices will, and call that saddle a constrained instanton. You get one for each slice. And then the idea is to do the full functional integral in two steps. You sum up first the contributions, the fluctuations around a given constrained instanton. And then second, you sum up all the slices, all the constrained instantons. And stated this way, it's clear that as long as you do things correctly, this method is just a convenient ordering, which variables do you integrate over first in the functional integral. In practice, one inserts a resolution of the identity into the Bath integral, where here lambda is the Lagrange multiplier, as lambdas often are, fixing you to the constraint slice, and zeta is the possible value of the constraint. And the idea then is to integrate over the quantum fields and the Lagrange multiplier first via some recoupling expansion, assuming it exists, and then one first integrates over fluctuations around some given constrained instanton, and then you integrate over the family. And this produces an integral representation here on this slide. Now, different choices of constraint will lead to a different choice of integrand. But the point is that since all we've done is insert one, the full integral better be independent of the choice of constraint. This is akin to something we're familiar with in ordinary diagrammatics. Some given amplitude, some given scattering amplitude can admit multiple integral representations. What's physical is not the integrand, but the full integral. We then adapted these techniques to Einstein gravity. To proceed, we need an intelligently chosen constraint. On shell, the solutions to the two boundary problem at hand are disconnected spacetimes with an even more infinite distance than usual between the two boundaries because they're disconnected. Turns out that we can find wormhole instantons if we constrain the length between the two boundaries. Using this constraint, we found several examples of wormholes. One of particular interest for this talk is this line element here, a 5D wormhole, which has S1 times S3 boundaries. Here, beta 1, beta 2 are the sizes of the boundary circles. Rho is a radial coordinate, and there's actually a whole family of these wormholes labeled by a parameter that I'm calling B. These wormholes are bottleneck geometries. They look kind of like this picture here. And roughly speaking, B controls the size of the bottleneck. Imposing that this space is regular implies a bound on this parameter, which in this case happens to be B greater than or equal to 1. That's what you need for the geometry to be everywhere regular. Now, all the wormholes we found, including the one on the last slide, have some features that are worth mentioning. Perhaps the most important one is that if we take the limit where the inverse temperatures, beta 1, beta 2, are equal and opposite, then these wormholes, what they become are Euclidean black holes, where the black hole mass is a function of this parameter b. If we made beta 1, beta 2 equal, opposite, and pure imaginary, you end up with a Lorentzian geometry, the double cone of Schenker-Stanford, actually, which is a time-like orbifold of the two-sided black hole. And so these wormholes that we're finding are, they're analytic continuations of black holes. Another fact is that, when you have a boundary in ADS, there's a boundary stress tensor. And if you compute the energies associated with these boundary stress tensors, they're actually the same. And they're roughly, b to the d divided by g Newton. You can exchange b for energy. And the renormalized action of the wormhole is actually very simple in terms of this energy. It's just the sum of the inverse temperatures, beta 1 plus beta 2, times this energy. Putting these facts together with our discussion of constrained instantanes, you get an integral representation of the wormhole amplitude. You originally integrate over all possible values of the constraint. That can be traded for b, and then for an energy, which I'm calling e prime. It's a dummy variable. And the integrand of this integral is just the loop expansion around a wormhole of fixed energy. Now, the classical action I mentioned on the last slide leads to this Boltzmann factor, this e to the minus beta 1 plus beta 2 e prime. And that, looking at that, it tells us something very important. It's that this wormhole amplitude is dominated by wormholes with the smallest possible energies. And in gravity, what that corresponds to is the limit where the bottleneck is pinching off. Curvatures blow up, and effective field theory breaks down. This tells us then that, alas, the ADS wormhole amplitudes are UV sensitive. They cannot be reliably computed in effective field theory. You don't give up, though. We'd like to, even so, reliably extract physics away from this pinching limit, i.e. to somehow be able to access the integrand in a meaningful way and study wormholes of fixed macroscopic energy. Now, the amplitude so far is a canonical ensemble quantity where we fix boundary temperatures. And so you might wonder, well, what if we somehow are able to fix energies instead? Is that some way of blowing up and staying away from this pinching limit? And it turns out the answer is yes. You can fix the energies if you do that up to some resolution scale, delta, then that allows you to select a particular wormhole. It becomes a non-standard saddle where one integrates not only over bulk fields, but also you integrate over boundary temperatures with some weight. That's what you need to go from canonical to microcanonical. And if the boundary energies are equal, then this non-standard saddle is precisely the double cone of Schenker-Stanford. You track with
Kristan,
this transformation.
Sorry, Kristan, this is your 5-minute warning.
Believe it or not, that's great. Okay, so this transformation from canonical to microcanonical, if you follow what it does to two-point function of trace e to the minus beta h, it turns it into this expression, the big one with the angle brackets, this sort of microcanonical version of spectral form factor. And how to say, if you look at the contribution from the wormhole then, that you get to this, the result is linear in time t, owing to some twist zero mode of the wormhole. This was something that was noted already in Schenker-Stanford. And the one loop factor around the double cone that we do not presently know. On bulk effective field theory grounds, though, one expects that to not scale with t, in which case you would get an answer that goes linear in t from gravity. Looks like a smooth ramp. In fact, it's very similar in functional form to the genus zero approximation of the same quantity in double-scaled random matrix theory, which I've also put just below it for comparison. We regard this as an evidence for a ramp in gravity, and so long-range repulsion. I should mention, well, okay, there's a second, more brute force way of fixing the energy that I'm going to adhere to my time limit and I can't talk about. Having constructed wormholes in Einstein gravity with negative cosmological constant, we now have the techniques to uplift them to 10D supergravity. So let's do so. Fortunately, it's very easy to do this, at least for Freund-Rubin compactifications of string and M theory. For instance, the 5D wormhole with S1 times S3 boundary that I mentioned above, it can be uplifted to a 10D wormhole with a form just a direct product, 5D wormhole plus 5 sphere of constant size in type 2D supergravity with constant axiodilaton, no 3-form flux, and then a 5-form flux that's just fixed by Gauss's law. Once you have these wormholes, you can, in 10 dimensions, you can begin to investigate the question of their stability, both against fluctuations of supergravity modes, as well as against non-perturbative nucleation channels. In our April paper, we undertook a partial analysis of perturbative stability, focusing on the lightest sectors, the most dangerous instability channels. And unfortunately, it's more involved than what I can give justice to here. There's a certain, yeah. So let me skip ahead. And what I can talk about in the amount of time given is potential brane nucleation instabilities. The main one to worry about here is, since there's a 5-form flux background, is the prospect that D3 anti-D3 brane pairs, which don't change the flux at infinity, those can nucleate in the wormhole. And indeed, in the probe limit, we find solutions for 3 branes which wrap S1 times S3 and sit at constant radial coordinate and angle on the S5. And within the probe limit, we find that for generic values of boundary temperatures and bottleneck size B, that the action of this 3-brane pair, the solution to the brane equations of motion, is negative, which indicates an instability. The wormhole with the brane pair on top of it has a lower action than the wormhole without. The physics of that is screening. It's likely to have the brane pair in there, and that decreases the amount of flux in between the branes by 1 unit, which in turn decreases the size of the wormhole in between. However, it turns out that as we decrease the size parameter B, there's a critical value such that smaller wormholes become stable against this nucleation. And this critical value is importantly macroscopic. There's smallish, but still ADS scale wormholes, which are completely stable against brane nucleation. Turns out that there's another way to lift this nucleation instability, namely to take the continuation of the boundary terms required to get spectral form factor, so beta plus IT, beta minus IT. And if we track what happens to the action of the brane pair under this continuation, we find that this instability is lifted by a finite amount of time evolution. It's an amount that's at most of order B. So we conclude that the double get in the limit where this T is much, much larger than beta is stable against brane nucleation. Okay, that's wormholes, what they mean. Here's a slide about factorization. I unfortunately missed the discussion earlier today, small kids and such. So I don't know what people said. The wormhole amplitudes in this talk appear to violate factorization of the 2 boundary amplitude into a product of 1 boundary amplitudes. And at some level, we've been trying, what we're trying to do is to sharpen the factorization paradox in ADS5 times S5 as best we can. In pure 3D gravity, it was perfectly fine to violate factorization. In fact, it tells us something useful, giving evidence for an ensemble interpretation. But in ADS5 times S5, which we expect is dual to a single instance of n equals 4, the matter is less clear. There's many questions.
Kristan, you're now into your question time. So
okay.
Up when you get a chance.
30 seconds. Okay. One question we might ask is whether or not there's a principle in string theory that just excludes the wormholes discussed from the start. I don't know how to begin answering that question. But if there is, I would say that would be a novel feature in quantum gravity. We're used to the statement that there's low energy effective descriptions, which can't be UV completed into string theory, that there's a swampland. But an exclusion principle like this, if it existed, would forbid us from summing over configurations within a low energy limit of string theory. There's also a very interesting suggestive recent paper of Saad-Shanker, Stanford, Yao, which Steve mentioned in his talk earlier this week. They're able to pose and solve a version of factorization paradox in 0 plus 0 dimensions using some collective field description of SYK fermions. Does that teach us about how we should think about, say, n equals 4 in strong coupling? I think it's not clear yet. The only known collective field description of n equals 4 is string theory on ADS5 times S5, which right now doesn't give us enough non-perturbative fine-grained control to analyze these problems. And I guess I can mention that the techniques, this will be my very last comment before questions, that the techniques in this talk allow us to construct wormholes, not just in ADS asymptotics, but in asymptotically flat geometries, like the full D3 brane geometry. And without a dual CFD interpretation, in that case, I'm unaware of some theoretical prior for factorization. And so, there's a logical possibility, as far as I understand it, that maybe somehow, some way, factorization is sealed in ADS, but perhaps not in flat space string theory. I don't know. It's an open topic for future investigation. And with that, I'll stop talking. Thank you so much.
Thanks very much, Kristan. Wonderful talk, and to Clifford as well. I suspect the given time, our organizers might want to move straight onto the discussion, but hopefully that will be a good chance for those with questions to ask them, and if not, in the Slack as well. So I don't know if Pedro, you'd like to take over at this point, or if we've got time for a question or two now.
We can have one question, and then let's move to discussion. Let's move at 25 to discussion.
Okay, I think the Hiroshi was first.
So actually, you might have already mentioned it, and I apologize if you missed it. But given the issues with the fact that there are no saddles and there are UV sensitivities, to be certain that these wormholes contribute, it would be nice to know some explicit example where you are constrained wormhole, how they compare with boundary computations, which I think I missed. Could you elaborate on this point?
Sure. So, how to say, yeah, it was fast. So indeed, there's no saddle point, conventional saddle point of Einstein's equations that yields these wormholes. And so there's a question, how sharp is this factorization paradox? How much tension is there? And this was the point of these slides where we try to fix the energy. So if we fix the energy, then we can get macroscopic wormholes. We're dealing with an unconventional.
Excuse me for interrupting, but I'm not asking about the bulk calculation. I'm asking, are there any boundary calculation for which you can actually identify the result of your calculation?
No. I mean, this is part of the problem. We don't, I mean, if we talk about n equals 4 at strong coupling, then I don't know of any way as of yet to compute the spectral form factors, say, in this regime. The only way that that I know of at present is through gravity, where there are these tensions with factorization.
Okay, yeah, that was my question. Thank you.
Okay, my apologies. Thank you.
So yeah, let's thank Kristan and Clifford again for those wonderful talks. I'm sure they'll serve as a beautiful warm-up for the lively discussion we're about to start. So with that, I'll hand it over to Steve and Jan. Yes.
Yeah, let me just say a few words. So